Okay, we're going to start chapter 9.5, the system of inequalities, by first graphing some inequalities one at a time. So say we had something like this: y is greater than or equal to x squared minus 1. And the way you start this is you graph it as if it had been an equal sign. Okay, so graph it like it had been an inequality. Y is equal to x squared minus 1. So I'll have a graph. And then when I go to put the graph on here, this is obviously a parabola that's been moved down 1. So it starts here, and it looks like this. Okay? So if it were an equality, it would look like that red line. Okay? But now we don't know, is above the red line a good solution to this, or below the line going to be the good solution. And so you talk about regions. One of the things we do is test regions. So we've divided the space into two regions here. There is this region that's kind of inside the parabola, and then there's another region that is outside the parabola, like this, okay? So we don't know, is the turquoise region the good region, or the yellow region the good region on either side of that line. So we're going to test and see which one is good. So I always like to test the regions by testing the point 0, 0. So let me go back over here. I'm going to test 0, 0. Okay? So when I put that into the inequality, I'm asking 0 is less than or equal to, with a question mark, 0 squared minus 1. So is 0 greater than a negative 1? The answer is yes, it is. So the point 0, 0, which is right here, is part of the solution, okay? It satisfies the equation. It's part of the solution region. So it and everything else in that region will be a solution. So our answer would be everything in here, okay? So the red then is the solution area. Normally we don't do the blue areas and the yellow, okay? We'll just show this red area as solution. Now it's important to note that this was greater than or equal to, okay? So greater than or equal to, or less than or equal to, you use a solid line, remember? And that works for this place too. If you just have less than, or you just have greater, you use a dotted line. That way you know whether or not points that are on the line belong in the solution or don't belong in the solution. Okay, let's try another one. All right, I want you to try this one, and I'll catch up with you. X minus y less than 2. So remember, you're going to graph it as if it had an equal sign, and then test which side of the line is the good solution, above the line or below the line. So give it a pause, I'll come right back. All right, there's my solution. Of course, we're not able to write the solution out because we are talking about a region, okay? So your answer will be a picture of your graph, okay, showing the region that is a solution. So mine is the green region, is the solution region. So how did I do this? I simply solved this original inequality for y, so I have it in mx plus b form. Don't forget, you need to reverse the direction of the inequality when you divide by the negative 1. So that gave me y greater than x minus 2. So negative 2, of course, is the y-intercept. I start there. The slope is 1, so I go up 1 over 1, up 1 over 1, and continue in that fashion. I used a dotted line because there's no equal sign here. Okay? So just a dotted blue line. And then I had to decide, am I going to shade above or below this dotted blue line? So I tested the 0, 0 point. When I test that, I come up with 0 is less than 2. That's a true statement. So 0, 0 is in the solution region. So everything else on the same side as 0, 0 will be a solution as well. So I colored it with my green, and that's my final answer. Okay, let's move on to systems where I have more than one inequality, and I want to know what region of my plane, my coordinate plane, will satisfy every one of my inequalities. Okay, so we're really looking for what region do the solutions of each one of these have in common? So we'll be looking for the overlap solution, okay? So let's go ahead and on the same coordinate plane, graph all three of these, in this case, equations. Now, the first one, I'm going to have to write it in mx plus b form, so this would be minus y is less than a negative x plus 2, or y is greater than x minus 2. Well, that looks really familiar. Okay, we've done this, so we know this. I'll start by graphing that one. Y-intercept, up 1 over 1, up 1 over 1, right? And so forth with a dotted line because there's no equals to. And I know I'm going to test the point, test 0, 0, 0 greater than negative 2. That is correct. So 0, 0 is a good point. And I'm going to shade on the same side as 0, 0 is. So that's my solution zone or region for just the first equation. So that was this one, black. Let me change my color. Now let's do this equation here in green. X greater than a negative 2. Well, that's easy. I don't have to solve for anything. I know that that's x equal negative 2 is talking about that vertical line at negative 2. So vertical line right here. It's going to be dotted as well. Dotted, dotted. That's the line. X equals negative 2. So which side of the line should I be shading? 0. Let's test the 0, 0 point. Is 0 greater than negative 2? So test 0, 0, 0 greater than negative 2. Again is a yes. So again I have a good solution for 0, 0. So I'm going to shade on this side, the same side as 0, 0 is from the line. Okay? Okay, so far you can kind of start to see what region has both good solutions. But I have a third one to deal with. So I'm going to deal with this one. Y is less than or equal to 3 is a horizontal line at 3. Okay, horizontal. This time it's a solid, because I do have the equal sign. I know I'm going to test the 0, 0. So 0 is less than or equal to 3. Again, 0, 0 is a good solution. So again, I have this as part of the solution zone. So I should be shading below the line. All right. It's a little hard to see. I get that. So let's go back and see if we can find, with maybe red, where all these lines kind of start to overlap. Where do I have everything? You're kind of looking for these vertices, okay? So when I look at this vertex right here, okay, and I look at this one, and I look at this one, I think I've got it. So if I draw this line with a dotted, that should have been dotted, my bad, and I go to the right, when I look at this solid line, and I'm below it, and I have this dotted line here, and I'm above it, then that's talking about all this triangle right here. And that would be my solution region for the overlap of all those three solutions. Okay? So, is it helpful to have different colors, pens, pencils, things like that, or highlighters? Absolutely. Okay, I just want to point out a couple of things that might happen as you're solving some of these. There is a case, it may happen, where you have no solution. And that kind of thing happens where you come up here, you draw one of your curves, maybe it's a line like this, it's dotted, and you realize you have to shade over on this side. And then you have another line, you come back for the second line, and it seems to be parallel, right? So you're looking at, even if it's solid, you're looking at a parallel line, and you have to shade above. Parallel lines never cross, so you'll never find a place where they will overlap these two regions, so that would be an example of no solution. The other thing that happens is the unbounded, where you start with a coordinate plane. Same idea, you could have a line, change colors, comes up here. This time you find you have to go above the line, okay? You come back, you do the second line, and you graph it, and even if it's not parallel, or if it is, you come up here and you have this line, and you find out that you have to shade below maybe. So where's the overlap? The overlap, of course, would be between the two lines that we're talking about. Might even go thicker. So between this line and this line, okay, in between will be this, but it doesn't have an infinite, well, just this one does have an infinite extension, where it's going to go on forever and ever in this direction, right? This one is eventually going to come to a close, okay, but in this direction, it's going to go on forever and ever. It's unbounded, which was very different from the triangle we had before, which was kind of a closed area, okay? So those are two kinds of things that might happen as you practice some of these problems. Okay, I'm going to go ahead and just include the 9.6 chapter as well, the linear programming. Linear programming is a technique for optimizing an objective function. Okay, so first of all, let me explain optimize. Optimize could be minimize it or maximize it. You always want to minimize, your losses, and you want to maximize your profits, kind of thing. So sometimes it's better to minimize, and sometimes it's better to maximize. So we use the word optimize. All right, so what are we optimizing? Could be almost anything. A lot of times you're minimizing the amount of material it takes to create a box around what you're shipping out, right? And so you save cost on shipping if you minimize that material, and things like that. So here would be the objective would be to minimize the amount of material, or the volume of the box, or something like this. So you have to have that. And so we're going to have an objective function, and we're going to call it z, okay? And it's going to be, for us, linear in both x and y here, okay? So we have this z, which is something that we want to minimize or maximize, and we know how to calculate it in general, okay? But what so often happens is x and y are constrained. Okay, there's certain limits on how big x can be, how small x can be, or how big y can be, or how small x can be. And there might also be limits on how the two interact with each other. Okay, if x is big, then y is small, or vice versa. They might have some sort of constraint between them. Okay, so when you look at the x and y plane, okay, there's no z on this, but you're just looking at x and y. And you come up with what's called a feasible region. So where are the regions where x and y could occur at? You get, for example, just some shape, okay? And in here are allowed values of x and y. So, and what we like to do is we need to find the vertices of this feasible region. Okay, so everywhere there's a corner, okay? So this blue line here meets the other line here, meets this line here, meets this line here, and so on. And so you find these vertices, okay? The vertices are very important. There's a very long proof. I'll save it maybe for later, but wherever the optimal value z is will occur at the vertices. So optimization is at the vertices. So that saves us the trouble. Well, it saves us the trouble of doing calculus, and it saves us the trouble of testing every point in that region to find out where z will be optimized, okay? So all we have to do now is test every one of the vertices. And whichever one of those has the optimal value, then that'll be the optimal for the whole thing, okay? So let's just do one of these so everything starts to make a little more sense for you. Okay, here's the question. We want to maximize the objective function, which is z, okay? We want to maximize that value. And we know z is given by 3x plus 2y. Now, hopefully this is bounded, so otherwise x would just be, you know, huge infinite number, y would be a large infinite number, and that would be the maximum. But of course it will be bounded, and here are the constraints, okay? So these are the constraints, and we'll need to graph this first, okay? So let's throw these up on a coordinate system. These first two are telling me that my feasible solution is in the first quadrant. You know, x is greater than 0. Let me switch colors. Okay. Y is greater than 0. So I can just get rid of second, third, and fourth quadrants. Don't even consider them. Okay. The next two are going to give me some lines, so let me work on those for just a second. This first one, 2y is less than or equal to negative x plus 4, so y is less than or equal to negative half x plus 2. Okay, so that's this one. So I'm going to graph that line with a y-intercept of 2, and then I'm going to go down 1 and over 2. Down 1 and over 2. So I'm here. So there's that line, and I'm going to make it a solid line because it's got an equal sign. Okay? I know I want to be less than that. Let me do a test point. Testing 0, 0 gives me 0 is less than 0 plus 2. Yes, that's true. So 0, 0 will be on the same side as the solution. It should be in the solution zone. So I'm going to go below this line with green. So far that's my solution, or my feasible region. I have one more to go though. Let's talk about this last one here, and that will be x minus 1 is less than or equal to y, so y is greater than x minus 1. That's a line with a negative 1 y-intercept. So sometimes you have to go out of the region to help you do the graphing. But then I'm going to go up 1 over 1, up 1 over 1, aha! And that's going to be a solid line as well. And it looks like that. Which side of the line? Let me test 0, 0. And 0 minus 1 is less than 0. Cha-ching, that's good. So again, 0, 0 is on the correct side. It's with the solutions. So we're talking about this area right here. Okay? So if I got out my red again and marked my vertices, and this, oops, stop right there, go up here, stop right there, and continue there. Okay? So this red zone right here is my feasible region. Now I need to figure out exactly what those vertices are. Okay? So obviously I've got vertice 0, 0, that one's pretty obvious. This vertice, I can pretty well tell from my graph, was 1, 0. This one here sure looks like 2, 1. And this one looks like 0, 2. If I was careful, if I had really good graph paper, I would know for sure. Yes, it was, because 0, 2 satisfies this equation, satisfies that equation, so that must be the point. I'm sorry, does not satisfy this one, satisfies this one. It had to be on the green line, right? So 0, 2 is on the green line, that's it. Okay, so those are my vertices. Now I'm going to take those vertices to my next page and test the objective function. So let's go to the next page. Okay, so I have my 4 vertices, I have my objective function. Now I have to calculate z for every one of these ordered pairs which represent my vertices. So in the first case, z is equal to 0 plus 0, it's just 0. In this second case, z is equal to 3 times 1 plus 0. Here, this vertex has 3 times 2 plus 2 times 1. 6 plus 2 is 8. And finally, I've got 3 times 0 plus 2 times 2, and I get 4. So I know what the z values are for every one of my vertices. Among here is my maximum. Remember, I'm trying to maximize z. That's going to happen right here. That's my maximum z. So z equal 8 at 2, 1 is the solution to maximizing my objective function z in this constrained region. Okay, so that's a good solution right there. Okay, let's try this next problem. It's got a lot of constraints though. And instead of maximizing this time, we're going to be minimizing. No big deal. They give me an objective function z given by 5x plus 7y. I'm not ready for that yet because first I'm going to have to graph my constraints. If you want to try this on your own and get back to me, that's fine, but I'm going to start graphing all these lines. So I'll graph all the lines and then work on the vertices. So pause it if you want to try it yourself, but here I go. I know it's going to be x and y are both greater than 0, so I'm going to have this kind of an xy coordinate zone. Okay, so give myself a lot of room here. Then, let's start with this first one here. That's going to be 3y greater than or equal to negative 2x plus 6, y greater than or equal negative 2/3 x plus 2. Okay, up to is a y-intercept, and I'm going to go down to and over 3. Okay? So that gives me this line. I don't even need to go further than that. Testing 0, 0, 0 greater than 2, no. So 0, 0 is not a good one for the first time. So we want to do the other side of the line that does not include 0, 0. So that's going to be this side. Okay? I'm going to try and keep things neat and only put one arrow so I know which side of the line I'm on. All right, then I'm going to try another equation. So let's try this one. That's going to give me 3x minus 15 is less than or equal to y. Oh, that's great. I've got a negative 15 y-intercept, and I'm going to go up 3 over 1, up 3 over 1, up 3 over 1. So, what happens? Let me just imagine when x is 1, where I'm at, okay? I'm having a little trouble graphing this, so I'm going to do it point by point. X equal 1, so y is equal to 3 minus 15, still way too negative. X equal 2 is going to be too negative. X equal 3, it's still going to be negative. 4, still a negative number. 5, okay, let's try x equal 5. When x equals 5, I've got 15 minus 15, y equals 0. Aha! So at least I'm on the graph. There I am. And then I can tell my slope is 3, so I'm going to go up 3 over 1. 1, 2, 3 over 1. Okay. So I'm right here. What is that? I'm going to go ahead and label that point. That's going to be a 6, 3, right? Let me label that. And I've got this line that goes on for a while. Okay? And this, of course, is 5, 0. All right. Now, which side of this line am I talking about? Testing 0, 0 is negative 15 less than or equal to 0? Well, yes, it is. So I want this side of my line. Okay, that would eventually include the 0, 0. All right, we're doing good. So we keep going. This just takes a while. Let's try a purple line. So I'm going to try this one. For that one, I've got y is less than or equal to x plus 4. Oh, I can do this one. 1, 2, 3, 4. Okay. Slope is 1. So I'm going to go up 1, over 1. So I'm right here. Keep going, up 1, over 1. Oy, oy, oy. Wish I had graph paper. Okay. So the line looks like this. Okay? Oh boy. So now I need to go above it or below the line. Testing 0, 0. 0 is less than or equal to 0 plus 4. That's a true statement. So 0, 0 is a good solution. I want to be below that line. Okay, that's good. Now, last one. Oh, let me, wow, that one's going to be trouble, isn't it? Let me keep going then. I better try a new color, though. All right, so this last one. All right, let me go to the next slide, do a little work, and then we'll be able to come back here and graph this. So if you want to see the explanation, go to the next slide. Otherwise, I got to keep moving. I've got to add it here. Turns out this one is going to be from here. It does hit the 1, 5 point, and it does hit the 6, 3 point as well. Okay, so both of those are on that line. The line will go like that. And when you test the 0, 0, you want to be below. So the feasible region is bounded by this line, this line, this line, over this way, up this way, and across this way. Again, go to the next slide and I'll do a little more explanation of that last line. Naming my vertices, the 1, 5, the 6, 3, the 5, 0. Remember this was a 3, 0. This was a 0, 2. And this is a 0, 4. So I have several vertices to test. Okay, moving on. So you might have to skip 2 to get on if you've already watched the other one. Okay, the idea here was you'll need 2 points to draw a line. So I'm trying to find 2 points that I can easily graph. So I went through and I just did a table of values. I let x equal 0, 1, 2, 3, 4, 5, 6 until I found 2 kind of ordinary points, if you will, whole number points that would fit on my graph. And I liked them especially when I got these points because I knew they were already points on the other graphs. So it turns out these were the helpful points to have. I put them on, I draw the line between them, and found all my vertices. Okay, so let's go on now to minimizing our objective function on the next slide. Okay, I listed all my vertices. I've written down what my objective function is, and I'm reminding myself that I do want to minimize. Sometimes we always think that maximizing is better, but not always. So z is 5 times 0 plus 2 times 7, so 14. Z is equal to 15. Z is equal to 25. Z is equal to 30 plus 21, which is, that's not a minimum. Z is equal to 5 times 1 is 5, plus 7 times 5 is 35. That's not going to be a minimum. And the last one has a chance. 0 times 5 is 0, plus 7 times 4 is 28. Nope. So you go back, you look which one of these has the smallest number for the minimum right there. So I have a minimum z equal 14 at the point 0, 2. So I know what the x and y values need to be to minimize that objective function. Woo!